Right. So continuity on intervals. We've talked about continuity at points, all right, at an individual point, but the notion of being continuous on an entire interval is pretty straightforward. It's just that you're continuous at every point on the interval. So if we take an open interval like this, a to b, this is using the parentheses, indicates an interval that doesn't contain its endpoints. A function is continuous on that interval if it's continuous at every x in that interval. This is the symbol that means is an element of the following set. So x is an element of this means that x is something that's between a and b. So here's my drawing of an open interval. All you've got to do is be continuous at every single x that's anywhere in that interval. Great. So like polynomials and all these rational functions and like for example the tangent function between negative pi over 2 and positive pi over 2 is going to be continuous on the entire open interval. Okay, but what about a closed interval? That's a little bit different. So a function f is going to be continuous on a closed interval, a to b, using the square brackets this time, if first of all it's continuous on the open interval, which means every point inside. And at a and b, we have special things happening. So one is the limit as x approaches a from the right of the function is going to be the same as f of a. So what I'm going to do is I'm going to get in here and I'm going to go ahead and fill in my 2 points so that now we have a closed interval. What we're saying is that the function needs to be, basically needs to, its limit needs to equal its value as you approach a from the right. So that's from within the interval. Okay, this is a limit from the right, has to be equal to the function value. And then the limit from the left at b, again approaching from within the interval that we're talking about, okay, has to be equal to the function value. So these two statements here are a lot like the definition of continuity, except they're using one-sided limits. So the reason we're using one-sided limits is because in this case for continuity on the closed interval, we only care about what's happening if you approach from inside the interval. That's why we use one-sided limits for this. And we even have vocabulary for this. This is called continuous from the right. And this is continuous from the left. So those are like defined. That's defined terminology that we can use if you want. So let's look at a quick example. I'm not going to go super in depth with this one, but let's just look at the function, which is the semicircle, square root of 1 minus x squared. This is if you take x squared plus y squared equals 1, the equation for the unit circle, and you solve it for y, you get plus or minus, you get like 2 possible functions, and so this is the top half of that unit circle. So the graph of this, we basically take the unit circle but only draw the top half of it, so like this. Now, what about at 1 and negative 1? Well, if you put 1 or negative 1 in here, you'll have squaring that will give you 1, and 1 minus 1 is 0. What's the square root of 0? It's just 0. It's not undefined. That gets confused sometimes. It is actually defined. It is 0. So the 1 and the negative 1 are fine. They're going to be part of this function. So that's what it's going to look like. So this function is defined on its entire domain, and that is a closed interval. So I'm going to write domain is everything from negative 1 to 1. If we have so what I'm saying is it's continuous at every point inside here, and it's continuous from the right at negative 1, and it's continuous from the left at positive 1, and that makes it continuous on its entire closed interval. I did want to show you what it looks like to prove that the function is continuous at some number, say c, between negative 1 and 1. Say if negative 1 is less than c is less than 1, so like there, for example, then what we can do is ask what is the limit as x approaches c of the square root of 1 minus x squared. And the way this works with the limit of a composition is that you can kind of take that limit and stick it inside the composition, so inside the square root in this case. This is only in certain circumstances, but this function, it is going to work because that limit is going to exist. The limit as x approaches c of 1 minus x squared can be evaluated because 1 minus x squared is a polynomial. It's going to be equal to its function value, so we can just take the c and stick it in there. So this would be the square root of 1 minus c squared, and that actually equals f of c. So that's showing that it is continuous there. Okay. By the way, this little trick that I did right here, this is described in more detail in section 2.3, which is what I'm going to go back and do after I finish 2.4. There's one more video for 2.4, so we'll get there. We'll get there soon enough.